Question number 36. Consider the given statements with respect to the molecular orbital theory. So first statement, the highest occupied molecular orbital in N2 is pi 2px equal to pi 2py. The second statement, bond order of N2 minus and N2 plus are identical. The third statement, C2 contains two bonds of which both are pi bonds. And the fourth statement, O2 2 plus and N2 are isoelectronic but they have different highest occupied molecular orbital. So students, the examiner is interested in C2, N2 and O2. So students, we know that C2 and N2 are going to have sp mixing, whereas O2 will not have any sp mixing. So due to sp mixing, the pi 2p bonding molecular orbitals are filled up first rather than the sigma 2p. So if we talk about nitrogen first, so it is going to have a configuration of sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px 2 equal to pi 2py2, then sigma 2p z2. So this is the configuration of N2. So in the first statement, the examiner is interested in the highest occupied molecular orbital of N2, so which is sigma 2pz2 and not pi 2px equal to pi 2py. This statement is incorrect. So we can look at the next option now. The bond order of N2 minus and N2 plus are identical. Yes, this statement is correct. N2 plus will have an excess of 5 electrons in the bonding orbital. So its bond order will be equal to 2.5. And if we talk about N2 minus, that will also have an excess of 5 electrons in the bonding molecular orbital. So the bond order will be equal to 2.5 again. So the second statement is correct. Let's talk about C2 now. C2 has 2 electrons less than nitrogen. So the configuration of C2 will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px equal to pi 2py, and both this pi 2px and pi 2py are going to have 2 electrons each. So these bonding and anti-bonding electrons will cancel out each other, and the bond order of C2 will be equal to 2, and it has 2 bonds out of which both are pi bonds. So this statement is also correct. So let's look at the fourth statement now. O2 2 plus and N2 are isoelectronic but they have different highest occupied molecular orbital. So students, the configuration of N2 we already have in front of us, whereas if we talk about O2 2 positive, so O2 2 positive will have a highest occupied molecular orbital of pi 2px equal to pi 2py. For O2 2 positive. And the highest occupied molecular orbital in N2 was sigma 2pz2. So students, statement 4 is also correct. So statement 2, 3 and 4 are correct, whereas the first statement is incorrect. So the option corresponding to this question is option 2. Let us look at question number 37 now. Consider the following E0 values. We have been given 4 different conversions and the E0 values associated with each of the conversion. Then the cell having the greatest EMF among all cells constructed using the above electrodes only has half cells as. So students, we know that E0 of the cell, it is equal to E0 of cathode minus E0 of anode when we are talking about the reduction potentials. So all of these values given to us are reduction potentials. So for the cathode, we need the highest reduction potential value. So D has the highest reduction potential value. And for the anode, we should have the least reduction potential value. So we can see that A plus has the least reduction potential values. So the cell which will have the greatest EMF will have 4 as cathode and it will have 1 as the anode. So the correct answer for this question is option 2. Moving on ahead to the next question. Question number 38. Acetic acid can form a dimer through hydrogen bonding. So we have been given the reaction for that conversion. At temperature of 25 degrees centigrade, the equilibrium constant Kp for the dimerization process is 10 to the power 3 and the bond energy per mole of H bond formed is 32.385 kilojoule. What is the change in entropy for the above reaction in kilojoule per Kelvin? So students, we know that delta G naught, it is equal to minus RT ln K, and it can be also written as equal to delta H minus T delta S, not values of course. So we have to find out the value of delta S naught. We have been given the value of K. We have been given the value of delta H naught indirectly. So let's try and figure out the value of delta H naught first. So it is given that the bond energy per mole of H bond formed is 32.385 kilojoule, which means that if we have to break one H bond, we have to supply this much amount of energy. So if we talk about the formation of the H bond, so it is going to have a negative value of this value, and there are a total of 2 hydrogen bonds being formed in the molecule. So the value of delta H shall be equal to minus 2 times the value given to us, which is 32.385. So this value will simplify to minus 64.77 kilojoule. Or we can also figure out the value of minus RT ln K. So this can be simplified to minus of 2.303 into 8.314, as we are dealing in SI units. The temperature value given to us is 298 Kelvin. And the value of log of Kp is equal to 3. This value is in joules, so we have to convert it into kilojoules as we are dealing in terms of kilojoules for delta H naught. So we have to divide this value by 1000. So this value will simplify to minus 17.117 kilojoules. Okay, so we can try and solve this expression. Minus 17.117 shall be equal to minus 64.77 minus of 298 delta S naught. So the value of delta S naught will automatically come out in kilojoule per Kelvin as the examiner has asked us in the question. So delta S naught is equal to minus 64.77 plus 17.117 upon 298, which gives us a value of minus 0.16 kilojoule per Kelvin. So students, the answer we are looking for in this question is option 3. Let us look at the next question. Question number 39. For the reaction A plus B in equilibrium with C plus D, the rate of reaction at any instant is written as this. If the equilibrium constant for the reaction is 1.87 into 10 to the power 4, then the numerical value of K is. So students, the rate of an equilibrium reaction can be written as rate equal to Kf into concentration of A into concentration of B minus Kb into concentration of C into concentration of D. So if we compare the rate to the expression given above, so we see that the value of Kf is equal to 2.8 into 10 to the power 3 and the value of Kb is equal to K, which we have to find out. And the equilibrium constant is given to us, K equilibrium, which is equal to 1.87 0.87 into 10 raised to power 4. So this should be equal to kf by kb. So 1.87 into 10 raised to power 4 is equal to 2.8 into 10 raised to power 3 upon the value k. So k can be written as 2.8 into 10 raised to power 3 upon 1.87 into 10 raised to power 4. Students, we can see that this is going to have a value less than 1. So its value is 0.15. So the correct answer for this question is option 4. Looking at the next question, let us look at question number 40 now. The dissociation constant for an acidic indicator HIN is 4 into 10 raised to power minus 6. Assume that the human eye can distinguish its color in acidic form when HIN is greater than 20 times the concentration of IN minus, and its color in basic form when concentration of IN minus is greater than 40 times the concentration of HIN. So we have to comment on the pH range of the color transition. So we have to first look at the dissociation equilibrium of the indicator. So HIN is in equilibrium with H plus and IN minus. The K indicator can be written as equal to concentration of H plus into concentration of IN minus upon concentration of HIN, which can be rearranged to be written as concentration of IN minus upon concentration of HIN is equal to Kn upon the concentration of H plus. So if we look at the condition in the acidic medium, so the ratio required to us is opposite of this. We can solve for the equality, which will represent the limiting case scenario. Okay. So in the first condition, we have the concentration of HIN upon concentration of IN minus equal to 20. So we can substitute the value from this expression. So we'll have concentration of H plus upon Kn is equal to 20. So we can take log both sides. Log of H plus ion concentration minus log of Kn is equal to log of 20. So we can convert this expression to minus of log Kn equal to minus of log H plus log of 20. So students, we can see that this is pKn and this is the pH. So pKn is equal to pH plus the value of log 20 can be written as 1.3. So substituting the value of pKn in this expression, the value of pKn will be 6 minus log 4. 6 minus log 4, 0.6 is equal to pH plus 1.3. So this is going to give us a pH value of 6 minus 1.9, which is equal to 4.1. So the pH has to be greater than or equal to 4.1. We can now look at the condition in the basic form where IN minus is greater than or equal to 40 times the concentration of HIN. So we can again solve for the limiting case. So IN minus concentration upon HIN concentration is equal to 40. So substituting the value from this expression, Kn is equal to 40 times the concentration of H plus. So taking minus log both sides. So this will give us a value of pKn. This will simplify to pH. The value of log 40 is equal to 1.6. So pK in can be simplified to 6 minus log 4, which is equal to pH minus 1.6. So on simplification, this will give us a value of pH equal to 7. So the pH has to be less than 7. So we can see that the color transition pH range of the indicator is from 4.1 to 7. So the correct answer for this question is option 4.